People have long dismantled whether we are distant from one another in the unparalleled spreading out of the cutting-edge universe. With an unwavering determination to discover if there is life anywhere besides our small blue planet, we have gazed at the stars and monitored the vast structures of galaxies. At last, that possibility has materialized. NASA's leading scientists discovered that something very important has been spotted on the periphery of our infinite time by the James Webb Space Telescope, our window to the universe. This amazing secret has been revealed. Life has been observed on a world that has been suggested to be Proxima B, and it alters everything. Examining the circumstances of exoplanets that transit in front of their stars forces us to learn more about the hidden worlds unveiled by the James Webb Telescope and the potential implications of the finding of life on Proxima for humankind's future in space exploration. Our comprehension of the cosmos is improved by the marvel that is the James Webb Space Telescope. Because of its superior development and unique placement in space, it offers researchers a unique perspective. Furthermore, it makes it feasible for them to focus on distant celestial bodies, planets, and stars in a manner that was previously unattainable. The primary mirror on JWST is one of its most noteworthy features. It is 6.5 meters wide, which is more than twice the size of the primary mirror on the Hubble Space Telescope, one of the most notable space exploration instruments in recent memory. Because of its enormous mirror, JWST is able to observe elements of the universe that science hasn't always been able to witness, including the tiniest light bursts from the furthest reaches of the cosmos. While scientists have long conjectured about what is beyond the reach of conventional telescopes, JWST has allowed them to view the real detail they have been imagining. Not only does JWST have a massive mirror, but it also has a number of state-of-the-art equipment that can detect a broad spectrum of light frequencies. An essential tool for taking pictures in the near-infrared portion of the electromagnetic spectrum is the near-infrared camera, NIR cam. Why does that matter? By penetrating dust and fog that obstruct visible light, near-infrared light enables us to view farther into the vast reaches of space. Astronomers can examine the development of stars and galaxies with an unparalleled perspective because to NIRCam's high-resolution imaging capabilities. Its main goals are to study the formation and evolution of galaxies, find and characterize exoplanets, and concentrate on the early cosmos and its mostly ancient light. In addition to providing insights into the enigmatic processes that shape our enormous universe and beyond, the detailed images taken by NIRCam show hidden intricacies and structures that were previously inaccessible to telescopes. This helps us to comprehend how large-scale systems emerge and evolve over time. But that is just one piece of equipment. Additionally, there is the mid-infrared instrument, MIRI, and the near-infrared spectrograph, NIR-SPEC. These technologies dissect the light emitted by celestial objects into its constituent colors or frequencies, enabling unprecedented degrees of research of stars and galaxies. By providing vital details about the temperature, structure, and chemical makeup of these objects, the spectroscopic approach helps astronomers better understand the intricate dynamics of stars and galaxies. It provides exact insights into everything it observes for researchers. Scientists can identify the elements included in a star or gas cloud by concentrating on the absorption and emission lines in the spectra, which reveals the building blocks of the universe. We can now comprehend the life cycles of stars, the development of galaxies, and the complex interrelationships among these celestial bodies thanks to this information. Furthermore, NIR-SPEC is essential to the study of far-off galaxies at high redshift. These galaxies give forth light that has come to us after traveling for billions of years, providing insight into the universe's beginnings. Astronomers may learn a great deal about the large-scale evolution of galaxies throughout cosmic history by analyzing their spectra, which also helps them establish the galaxy's age and chemical composition. MIRI on JWST is specifically designed to investigate objects releasing infrared radiation at longer wavelengths in the mid-infrared region of the electromagnetic spectrum. We can investigate a wide range of processes with this capabilities, including star formation and the identification of exoplanet atmospheres. The investigation of the dusty environments where stars are created is one of MIRI's main objectives. These dense dust clouds are permeable to infrared light, which enables MIRI to look into the darkness of space and observe the formation of stars and planetary systems. Astronomers can get crucial insights into the workings of these star nurseries thanks to the precise pictures and spectra it takes in the mid-infrared range. That's not all, though. By observing in the mid-infrared, MIRI is also crucial in the search for and characterization of exoplanets, as it is able to identify and analyze the feeble heat emissions from exoplanet atmospheres. The research of exoplanet composition, temperature, and possible habitability is greatly facilitated by this capability. Our understanding of the presence of water vapor, carbon dioxide, and other essential molecules, elements that may support life, is aided by MIRI's observations. How does the James Webb Telescope search for indications of subsurface activity? Spectroscopy and transit observations are two of its main techniques. Spectroscopy, a method that lets scientists examine light emitted or absorbed by an object to ascertain its composition, is at the core of this investigation. Spectroscopy plays a crucial role in unlocking the molecular mysteries concealed in the atmospheres of exoplanets. JWST eagerly anticipates a transit event, which is a spectacular event in which the exoplanet appears to pass in front of its host star when it is in focus on an exoplanet. JWST watches the starlight travel through the exoplanet's atmosphere as this is happening. Equipped with cutting-edge equipment, JWST collects this important light, with MIRI prevailing in the mid-infrared spectrum and NIR spec ruling the near-infrared. They work well together to cover a wide range of frequencies that are necessary for in-depth research. One may ask themselves why it is important to photograph starlight during a transit. Well, this starlight provides important details on the makeup of the exoplanet's atmosphere. Light interacts with different molecules in the exoplanet's atmosphere as it travels through, creating unique atomic traces or fingerprints on the starlight. JWST then applies its spectroscopic capabilities to a thorough analysis of the filtered light. By analyzing the absorption or emission lines in the light spectrum, scientists are able to pinpoint the precise compounds that are present in the exoplanet's atmosphere. Because each molecule has an own set of spectral characteristics, it is possible to identify and manipulate them to precisely piece together the whole narrative. In order to achieve accurate results, JWST performs a great deal of modeling and analysis. To match the observed spectrum features with their corresponding molecular identities, it uses complex simulations and reference spectra of known compounds. To interpret the atmospheric language of the exoplanet, see it as cross-referencing a celestial dictionary. Determining which particular molecules are present is only the first step. Looking for clues about activity below the surface calls for a more sophisticated strategy. Researchers search for chemicals known as biomarkers, substances that may be connected to life. Gases that are necessary for supporting life on Earth, such as oxygen, methane, and water vapor, may be included in these biomarkers. To evaluate the general habitability and any potential indications of biological activity, further information and data are yet required. JWST uses additional observational methods in addition to its spectroscopic capabilities to improve the hunt for life.